What if it rained food? What if Earth was a cube? What if we had 9 lives? What if bits could fly? It's absurd. If money grew on trees, if we didn't have knees, if we walked through life slightly magnetical, it's absurd. Absurd Hypotheticals.
Hello, everybody, and welcome to Absurd Hypotheticals, the show where we overthink dumb questions so you don't have to. I'm your host, Marcus Lehner, and I'm joined here today by Chris Yee and Ben Storms. Say hi, guys.
Hey, I'm Chris.
Hey, I'm Ben. And I have some news.
Ooh, I like news.
I got married last week.
Ooh, congratulations.
Thank you.
That is big news.
Yeah, it's kind of big news.
I acted surprised, but I knew that already.
Yeah, both.
I already knew that too.
Yeah, it's okay. This is also somewhat surprising, maybe partially to Marcus, because he's in my wedding party and he wasn't there.
I was busy. I had shit to do.
Yeah, so
prepping for this podcast. I need to learn about stuff.
Right. So as I'm sure has been mentioned at some point on this podcast, my wife is from Trinidad, and she's over on a fiancé visa. And as is now well known by everyone because of the existence of the show 90 Day Fiancé, you only have 90 days after they enter the country to get married. And, you know, she got here in September, and our wedding is in January. So you can do the math. You can figure that one out.
So did you realize this beforehand, or did you just
we realized it ahead of time.
Okay.
and decided to just so it's like what it comes down to is that it makes more sense to do it now anyway, because like she can't work immediately.
Right.
She has to get like a temporary work permit before she actually gets the green card. So that process can only start once we're actually married. So we kind of wanted to get that going quickly as it was. So yeah, so we went to Boston City Hall, just like during the day on a Friday. It's really funny that just like apparently there's like 4 days a week. There's, I want to say, two 2-hour-long blocks where they just do weddings in the city clerk's office, and just that entire time is just like people going through getting married, which must be super fun for people who work in that office. Like,
so did you have to like wait in line?
No, there was a group staying around in like the waiting area, also all dressed up for a wedding when we got there, and then there was one coming in after us, but it wasn't like a line. You sign up ahead of time. You like book a time.
Okay.
Do you think there's a lot of people that like don't want to do like a church officiate and don't realize that you can just like get that like service online, and so they just like plan to go to the clerk office and then go to like the wedding party?
Oh, probably. Yeah. I mean, to be fair as well, it is like if you are using a non, does it for a living officiant, it takes a lot of stress off of them if you get it done ahead of time, because they don't have to worry about, the legal part. They're just talking for a little bit at that point, which is easier for them. But no, it was actually surprisingly real feeling little ceremony. We did the vows and everything and exchange rings and all that. So it was cool.
Are you gonna say the same vows at the other wedding? Are you gonna change them?
We're gonna so they were just like the stock vows, We're gonna write our own for the full wedding.
So was there anyone there when you got married?
Yeah, it was our parents.
That you knew?
It was our parents. Okay. Our parents, yeah. Sure, her parents flew up from Trinidad. Mine drove down from New Hampshire, which is a lot less dramatic. Yeah, it was good. And it was actually really fun because then we were just like walking around Boston in, clearly we just got married. Like I was in a suit and she was in a like a white jumpsuit and was carrying a bouquet. And so we were walking around and people were just kind of like kept constantly saying congratulations. Yeah. It was kind of fun. Actually, the best part.
We have to. It's like built. It's like hardwired.
Well, and so the best part, we were walking like over near City Hall still, and there was a group of what we believe, it was definitely a large group of Asian like teenagers. We're pretty sure it was a field trip. Field trip is sort of putting it lightly. Group from like Japan. And we were walking by, and there was like an instructor up on a wall, like talking to them. As we walked by, she started waving her arms and yelling congratulations, and then applauding. And then all of them, a group of like 40 of them, all in like, the matching uniforms, turned around and started clapping. And it was like kind of cool, but also super weird.
But like also super like, please let me continue walking.
Right. We were like, thank you. Keep on walking.
Did you like? Where did you go? Where did you go to eat afterwards? Like, I'm kind of curious, like the dynamic, like the image of just like walking in dressed for a wedding to like a regular restaurant.
We did like a the kind of this is one of the things where I don't want to like sit. It was Bostonia Public House, which is a reasonably upscale but still go there for lunch place.
Yeah, it's a
Okay,
pretty
yeah.
nice restaurant.
They have, like
Nice
yeah.
restaurant.
they have, like lobster rolls and stuff, like that kind of stuff,
Yeah, they had white tablecloths and,
Yeah.
servers
did.
nicely dressed.
They did a champagne toast for us because we had said we just got married.
Oh, very nice.
Which was nice as well, yeah. So, shout out those fine people.
Very cool. But now I don't care about it anymore because now it's in the past.
Yep,
So now we
forgotten
have to
completely.
talk about hypothetical questions because that's what we do here.
We don't talk about marriage for an hour.
No, we don't talk about marriage. We're not a marriage podcast.
Aw.
We lack the expertise. Chris, neither you nor I are married, and Ben's been married for like 18 minutes.
Yeah.
We can speculate.
We have slightly more expertise in this question that we've now, studied for like a week. So now we're subject experts. And our topic this week is actually from a listener. Thank you, Luke Aschenberg, for this question. And it is, what if an element from the periodic table was missing? So what I did was I took my 118-sided die and rolled that, and critically failed that roll, so I rolled a 1. But no, I decided to go with what I assumed to be the most problematic choice, which was hydrogen.
Yeah.
Element
so
numero uno.
We each picked our own elements. That's how that worked.
Yep, we each picked our element. I picked hydrogen.
Yeah.
Mostly because I assumed this would break the most things. It turned out it breaks a lot of things.
I would think so.
So, in fact, I'm going all the way back to the Big Bang because it took me a while to figure out if the universe would even exist. So, Big Bang happens. All the matter in all the universe is compressed into a tiny infinitesimal point, and that thing explodes. And so, for the first fraction of a second, the entire universe is what they call is a group of quark gluon plasma, which basically is just energy. It is literally a trillion degrees Kelvin at this point in time of the universe. And what is happening is that the very tiny quarks and things that make up matter are trying to form, except they're being immediately annihilated by the anti-quarks and the anti-gluons and all the antimatter. So that's about like 50-50 matter-antimatter, and they are just annihilating each other. And it actually takes not long, because this is all like on the scale of like fractions of a second, but until enough energy dissipates, you can't even form the basic building blocks of elements, the neutrons and protons. So after about 3 minutes, the universe is now cooled down from a trillion degrees into a nice toasty 1 billion degrees, which I'll classify, I guess, as universe lukewarm. So this is the first time where elements even have a chance of forming. Actually, not even elements yet, only like the nucleuses of the elements, because all the electrons are still in a form of plasma. They're too high energy. They're just like zooming around everywhere. They're not connecting to any individual nuclei, which is good because technically, if there's no electrons around it, it's not stable. It's not quite hydrogen. I'm not counting it. So my first problem with hydrogen was that in order to form elements, basically what you have to do is you have to get protons and neutrons to collide together into one big nucleus. And then, you just keep adding protons and neutrons until you get up to whatever element you are. So like carbon is element number 6. It has 6 protons and some number of neutrons. And there'll be variations. It could be like carbon 12 or carbon 14, which has different numbers of neutrons. So the thing is, they don't really combine. Like, you won't get 3 to collide at once. You can only like do 2 together and then, another 2 together and then another 2 together. So you couldn't actually make helium at all because 2 protons won't go together. So 2 protons just by themselves won't go together. You need at least 1 neutron to kind of cling it together a little bit because they repel each other. So at the very start of the universe, you can make what they call deuterium, which is 1 proton and 1 neutron that is pushed together. And now what can happen is that this deuterium, which is 1 proton neutron, can now collide with something else, with either another proton to make helium-3, or it can collide with another bit of deuterium to make helium-4, and now you're starting to put together the basic building blocks of elements. It's worth noting that it's actually, so this is 3 minutes after the Big Bang. It's not until 400,000 years later, when the temperature is down to a very cool 4,000 Kelvin, where you can actually start making stable elements. So kind of what happens is, for the most part, is, you'll have these 2 element thing, like deuterium form with like a proton and neutron, or 2 neutrons, or whatever you want to put together, and they'll basically just immediately get zapped by gamma radiation that's everywhere and explode off into 2 different things again. So it's really actually a low chance of these things forming until you start getting to lower energies where more stable reactions start happening. So after about 400,000 years, our actual universe was made up of about 75% hydrogen, 25% helium, and no other elements. No other elements have formed at this point. Because everything else is either isn't stable enough at the energy levels that they're at, because it's still very hot, so higher elements are unstable at higher temperatures. Heavier elements are unstable at higher temperatures, so they'll break apart into hydrogen and helium. So you don't get anything else besides those two for a while. That while being 100 million years. So after 100 million years, the universe has finally cooled down enough that hydrogen and helium, in our case now, since there's no hydrogen being formed, only helium. We only have helium floating around.
It's going to be a lot of helium.
It's going to be a lot of helium.
The universe is going to sound hilarious.
That's the only side effect of having only helium.
Yep.
Yeah, that's it. And everything else is fine.
Real squeaky universe.
We live in a big helium balloon. But no, that's not. We're not quite out of the woods yet. So now, the way the universe goes is after 100 million years, we have all this mass floating around, and now it's finally, just due to gravity, now the mass are slowly starting to coalesce and form the first stars. So the way the stars form is that a bunch of matter comes around, all this helium and hydrogen comes together, attracts itself, and now the force of gravity is pushing it denser and denser and denser into this ball. And as the ball gets pushed together, the center of that ball heats up until it gets to about back up to 7 million degrees Kelvin, where now you're starting to get nuclear fusion occurring. And generally the way stars work is that they are fusing elements together to release energy. And the reason that they release energy is that when you actually combine like two hydrogens together to make helium, the mass of the helium is actually slightly less than the two hydrogens by themselves. So you've managed to, destroy that amount of matter or convert that amount of matter into energy. Matter can neither be created nor destroyed. Important point in physics. But yeah, so stars generally run on hydrogen fusion, which I was like, crap, because we just got helium. So stars can't really be going if I'm combining two hydrogens into heliums because I don't have any hydrogens. And so I was doing some more research. Turns out stars do other fusions.
Do. Had to point it out.
This is a science goddamn podcast, Chris.
I have to point it out.
You absolutely
It's a
do not
law
have to
of
point it
nature.
out.
No, it's in the rules.
Yeah.
It's in the rules.
God, come listen to this real smart science podcast. They say do a lot.
Do.
Anyhow, so it turns out, so for example, our sun, I'll use that as an example, a fairly typical star, 80% of the reactions that occur in the sun are hydrogen into helium fusion reactions, with 20% of it being actually, well, I'm going to say helium into helium reactions, which is basically helium-3 with one neutron hitting a helium-4 or like another neutron, and they actually go through a couple combinations where heliums will collide and combine into like going from helium-3 to helium-4, or two helium-3s colliding and making some other stuff. I didn't quite get it because 3 plus 3 made a 3 and a 4, but a 3 and a 4 also made a 3 and a 4, and sometimes 3 and a 4 made a 4 and a 4. So I'm not sure where all the neutrons are going. But there's only so many diagrams of helium that I was willing to look at. But interestingly, so 20% of our sun's reactions are helium, but it actually creates 50% of the energy that our sun emits. So half of it is the hydrogen and half of it is the helium fusion. So theoretically, if it was just helium, I guess our sun would be half as bright. I'm not quite sure if it's just helium how it works, because nobody's answered this question with a real physics degree. But you could still have fusion going on, which is cool, which means we can still have stars that are like our sun. They will last a less amount of time, though. So the hydrogen and helium fusion reactions are what they call the primary phase of the star. And they basically are in here until the helium-3 and the hydrogen numbers are depleted. So once it runs out of that fuel, now it starts becoming a red giant. And so the amount of fusion that they're doing, they're now combining heavier elements. And now it's actually helium and helium are combining to make carbon in the center of the sun. And so it's still a fusion reaction, still emitting energy, but not as much energy as the other force in the sun that are trying to make it expand. So it's the sun starts to expand. And to put into perspective is when our sun hits this point and starts to become a red giant, the outer diameter of the sun will actually reach the Earth. The Earth would be within the diameter of the sun. So red giants get huge. And so the sun's basically taking all this helium, it fuses it into carbon, and now make the core denser and denser and denser. And now carbons will fuse together, and actually goes all the way up to iron, So iron is the highest element that stars will create by fusion. So you go all the way up to an iron core of the sun, element number 26. And at this point, the energy of the fusion reactions are no longer sustainable. Then the star collapses in on itself, creates an incredibly dense core for like a very fraction of a second, and then it explodes. This explosion is actually where all of the rest of the elements come from. So basically, you start off with hydrogen and helium, just in space. They kind of come together into a star. Then that star starts heating up and starts combining them into slightly bigger and bigger elements until it gets up to iron. And then that iron explodes, and that explosion is what creates all the other elements in the universe.
So all this already happens with hydrogen, but without hydrogen, it just happens faster?
I'm not exactly sure if it would happen faster or slower. You could still do fusion reactions with helium. The physics gets a little wonky because it's really just about putting nuclei together. Like the helium is 2 protons and 2 neutrons, or,
Right.
And now it's hard to have like you can't have single protons, and like you can't have single protons because that would be hydrogen once it's like in a stable form. So you only have 2s to combine with each other.
Right.
So now that I say that out loud, maybe you don't get odd numbered elements when you're in the star.
It's like getting rid of the penny.
You're getting rid of the penny. You don't need it. It's too small. We don't worry about that element anymore. But basically, the main conclusion is that you could form stars, they could perform fusion, they could explode, so you have a universe that can exist.
Yay.
I like that your point here is stars can still explode, so we're okay.
It's usually the opposite,
Right.
of us being, well, we're not okay.
Usually that's the end point of our question. It's not the start of it.
Yeah, so I took a little bit of a look into what our universe might look like without hydrogen. And so the first thing I was looking at that I remember from high school chemistry is that the elements form compounds based on how many valence electrons they have. So, oxygen has 6 out of 8 valence electrons. So it's looking for 2 elements with 2 electrons that it can combine with to make, nice stable orbits. It wants to get 2 electrons from somewhere. And a hydrogen has 1 electron going around it, and it wants a second one, so it kind of combines with oxygen. So 2 hydrogens combine with the oxygen to make H2O, which we know is water.
Which is important.
Yeah. So with the periodic table, if you take 1 step downwards, in the same column, all the elements are missing the same number of valence electrons. So typically, they tend to act similar. So right below hydrogen, element number 3 is lithium. And I was like, all right, so lithium should be like fairly close in properties to hydrogen. Like it's missing, it has just 1 extra electron on the outside orbit, and it's just trying to make bonds the same way. It'll combine with the same elements. So I was looking what lithium 2O was looking at, lithium oxide. And I was trying to see like, okay, so how useful is lithium oxide for us? And so I kind of went on Wikipedia, and according to Wikipedia, lithium oxide is used as a flux in ceramic glasses. It reacts with water and steam, forming lithium hydroxide, and should be isolated from them. So it can be used in ceramic glasses to make colors. It says don't mix it with water and steam, which we don't have to worry about because we have no more water.
That's a plus.
And then lastly, so after that, it just says its usage is also being investigated for non-destructive emission spectroscopy evaluation and degradation monitoring within thermal barrier coating systems. It can be used as a co-dopant with yttria and zirconia ceramic topcoat without a large decrease in expected service life of the coating. And so it's really not super useful. It really doesn't do anything for us anywhere. Lithium oxide has basically none of the properties of water that I'd kind of be hoping to replace things with, where I'd be kind of hoping to just be like, oh yeah, no, it just wouldn't be hydrogen, it would just be lithium and it would serve the same role. None of that happens, and that's mostly because of what they call hydrogen bonds. And hydrogen bonds are, going back into chemistry, different than covalent bonds. So covalent bonds are typically what you do. It's when the electrons fill in the outer orbits. Hydrogen bonds are different. Basically, the way the hydrogen bond works, hydrogen is super tiny. It's got a low mass, it's got 1 proton, and then the 1 electron. And when it goes by like an oxygen molecule, which is much bigger and has a negative charge, the oxygen kind of sucks up that electron. And they share it, but the oxygen is very greedy and kind of holds onto it closer to the oxygen than the hydrogen. Now, what it causes that is that now the hydrogen nucleus, which is positively charged, is kind of out on its own and has a little bit of a positive charge. And so now that positive charge will unbalance the whole charge of the whole molecule. So if you might know, water is polar, which means one side of a water molecule is positively charged, one side is negatively charged. And the hydrogen bond is the hydrogen's kind of lining up and making those connections. So they're weaker than normal bonds, but they do important things like they give water its surface tension. It's the reason why water is such a good insulator. It's the reason water can dissolve things. And because lithium and all the other elements going down from there are heavier than water, heavier than hydrogen, they have another shell of electrons that insulates it, and it won't form like the type of hydrogen bonds. It won't form hydrogen bonds. Not because it's not hydrogen, but because it doesn't work the same way.
It doesn't have that polarity.
Yeah, it doesn't create the polarity because the lower shells of electrons shield that extra positive charge from really making a difference. So basically, you don't have water. You don't have anything like water as we know it. Other important things, DNA is held together by hydrogen bonds. Organic proteins also held together by hydrogen bonds. So really you have none of the organic life that we would know without hydrogen. So yeah, we would have a universe, but we just would definitely not be in it.
It's better than I thought it would be, though.
Ben, what did you do?
So, on a similar note to your ending point there, I looked at what would happen if all carbon disappeared.
Oh, that's another one of our buddies, huh?
Mm-hmm. Yeah, so that's the thing that makes up organic life with the hydrogen. So basically, all life as we know it would disappear. So that's my real quick answer. Yay, boom, done.
All right, Chris, you're next.
But for real, so that sort of makes, there's obviously a pretty big assumption here, which is that all life has to be carbon-based. Which this is something that's like even amongst scientists kind of debated if that's necessarily true. So Carl Sagan, well-known astronomer / just cool science dude, he called this carbon chauvinism, which is basically just the idea that no, I know.
Elitist carbon trash.
By the way, Carl Sagan, every time I look up like anything related to Carl Sagan, it reminds me I need to read more of Carl Sagan's stuff because he is so just awesome. But basically, carbon chauvinism is the idea that nothing else could ever be the basis of life because carbon is just really, really good at it. And it's all we've ever seen. But sort of his point is that it's really, because the universe is so, fucking giant, it's really hard to say that any statement applies to all, any statement applying to all life on Earth could ever apply to all life throughout the universe, Although I will say that there was a Rolling Stone interview where Carl Sagan did admit that he is actually a carbon chauvinist. So he just wanted to put out the possibility. Also, in that interview, there's this wonderful exchange where they're talking about sort of the issues with like some, alien species and like popular culture. And it leads to this exchange. So the interviewer says, enormous insects and Earth-like environment are likely to exist only in human fantasy because insects breathe by virtue of diffusion, which is not efficient enough to keep a big creature alive. To which Carl Sagan says, that's why motion pictures like Mothra are flawed. The interviewer says, I haven't seen Mothra. And then Carl Sagan says, and this is the greatest box quote ever, I haven't either, but I understand it's a very large insect. Maybe I'm wrong. If it's not a large insect, then I don't object to it. I love Carl Sagan.
Get Mothra. Carl Sagan, if it's not a giant insect, doesn't object to it. Wait, shit.
It's so good. Anyway, so like I said, we kind of assume that all life has to be carbon-based. So why is this? For this, I looked at, there's this paper by Norman R. Pace in the 2001 Proceedings of the National Academy of Sciences of the United States of America called The Universal Nature of Biochemistry. And it kind of lays out a lot of sort of the baseline facts and assumptions of biochemistry. And there are a lot of reasons that carbon is sort of the assumed requirement. The biggest one goes back to what Marcus was talking about with, molecular bonds. So, he mentioned it. Atoms want to fill that outer shell of electrons. Carbon basically has 4 in its shell and needs to get to 8. So that's really hard to do without sharing electrons. So it just bonds with everything. It is super, super horny for bonds, which is important because in order to get life, you have all these really complicated structures you have to do for things like proteins and DNA and RNA that you just need these really big molecular structures for. In order to get that, you need to have both these multiple bonds and double and triple bonds where you're sharing multiple electrons, which is just much easier to do when you have 4 free electrons the way that carbon does. There's some other things in there as well. There's things about the fact that water is a solvent for it, which all the life we've seen obviously uses water as a solvent. But the biggest takeaway from this is just that it's that for free electrons, it really leads to carbon being sort of the building block of life. So similarly to Marcus, if you move down the periodic table, you get to silicon. And silicon life is something that's actually been sort of posited by both scientists and like science fiction for a while. I'm pretty sure there's actually, I didn't look it up specifically, but I vaguely remembered this and saw it mentioned a couple times. There's like a Star Trek episode, like original series Star Trek, where there is some sort of silicon-based like rock monster or something. So silicon is probably our best option. It also has 4 free electrons and theoretically can make these complex molecular structures. It actually has sort of happened in a laboratory setting. There were researchers at the California Institute of Technology who, it wasn't pure silicon, it was like a carbon-silicon bond where they were able to make organic compounds that were like an organosilicon compound.
It's kind of cheating if carbon's in there.
But what they were able to do, so originally they just made like enzymes that could generate these compounds. They were also able to make E. coli that was genetically engineered to produce the enzyme that would then generate the compounds. So even though, it is, I agree, somewhat cheating that it has carbon in there still, it does show that it is theoretically possible for life to create silicon bonds itself. Like, it is at least theoretically possible. We're getting once again into this, like, the universe is really big. If we can make it happen, it could happen on its own somewhere.
Right. I'm not gonna fault you for mixing in the hydrogen.
Yeah.
All my research for like my lithium oxide things kind of hit a dead end because everything down that column, if it's like, lithium 2O and you put it anywhere, it just likes to grab hydrogen and make like one lithium, one hydrogen, one oxygen, and it's like make 2 of them and just like split it and making go halvesies with hydrogen. So it's like any reactions that happen involve hydrogen. I'm like, stop it, just stay together.
Exactly. So there are a lot of issues with the idea of silicon life. A couple of them. One, silicon is just, even though it has the 4 free electrons, it is much worse at making bonds than carbon is, particularly double and triple bonds, which are kind of necessary for life. The big reason, the atom itself is larger, and then because it's a further out shell being used, the force is weaker. So it's just the bonds it makes are much less strong, which when you're making life, strong bonds is kind of helpful.
That's deep, Ben. That's deep.
Yeah, I know, right? The other thing, too, is that the long chain hydrogen silicon compounds, which are sort of similar to like the alkane hydrocarbons that we have, are highly reactive with water and also spontaneously decompose, which is also pretty bad for life.
Oh, yeah. I mean, we can spontaneously combust, but spontaneous decomposition seems way less fun.
Yeah, it's not great. There are ones that are like alternating silicon and oxygen instead of direct like silicon bonds, which is silicones. Those are more stable, and they're actually very stable. They're actually more stable than hydrocarbons in a like sulfuric acid environment. So theoretically, it could happen in unlike those conditions. I think there was also something involving both like high and low temperatures. Somehow both got brought up. I know like the silicon compounds are similar to sugars. Are soluble in liquid nitrogen. So theoretically, they could be like very low temperature biochemistry involved there somehow. So I guess one of the big things they sort of pick up here is that, obviously this would probably not happen on Earth if we were going to have silicon life, but it could theoretically happen somewhere. One big problem with silicon life, even aside from all of the decomposition and everything. So one nice thing about carbon is that like during respiration, when energy is released from a carbon compound, it's oxidized, and the waste product is carbon dioxide, which you just breathe out. That's great. If silicon compounds do the same thing, the waste product is solid silica, which is just like silicon sand.
Oh.
Which is a little less fun to, deal with. So that's like sort of something we have to, get past. A little awkward, but not a showstopper.
I'm not passing sand, Ben. I'm not gonna pass sand. I can't imagine any fate that's worse.
Yeah, it's not great. So silicon, technically possible, not great. Are there other options? Kind of. There is one other thing I found that was really cool. By the way, a lot of what I did came from this excellently named Wikipedia page that was perfect for the show, Hypothetical Types of Biochemistry, which is just like great. It's so much fun. But just metals, actually. There's a group at Glasgow University actually made self-assembly of tungsten polyoxymetallites. Wow, got that first try.
You assume.
Yep, listener, first try, I promise, no editing there. They actually self-assembled into cell-like spheres, where they basically took these metal oxides and effectively replicated cells using it. They made like these spheres out of them and then made smaller ones inside to replicate like the different, structures in cells. And by altering the metal oxide content, they could actually get them to act as a membrane the way that cell walls do. And the early results suggested they could actually make a membrane that splits water into hydrogen ions, electrons, and oxygen when illuminated, which would let them do photosynthesis with it, which is pretty cool. The guy behind it said that he hopes to induce them to evolve into fully inorganic, self-replicating entities, which I'm pretty sure is how we die in a lot of science fiction, so maybe don't do that. But, like, get close and then report about that, but not, like, all the way.
All gonna be lung sand all the way up to the top.
This is basically... Have you heard, like, the gray goo apocalypse scenario?
I've
No.
heard the basic idea of it.
So the idea, this is basically like what this would lead to eventually. The idea of gray goo is that eventually someone will make some sort of like, it's basically self-replicating nanomachines that convert matter into more self-replicating nanomachines. The idea being,
that's not good.
Yeah, so the idea being that you do it where it's like, oh, we can, make these mining robots that can make themselves while they're mining, and we can mine really fast, whatever. But then some switch gets flipped accidentally, and they just see everything as a source of resources, and then suddenly the planet gets devoured by self-replicating nanomachines. That's basically what this is going to do, so that's cool. So maybe don't get all the way there, or at least if you're going to, wait until I'm about to die so I can see it, because that'd be kind of cool. But like only like right at the end.
Be a cool way to go.
Yeah.
But I mean, it would be the cool way to go because everybody's doing it.
Exactly. You're right. It's the hot new trend. And then finally, there was one actually in the section of hypothetical types of biochemistry called non-planetary life. In 2007, there was this guy Vadim Sidovich. I'm guessing here.
Not as confident.
I'm not at all. So they proposed that lifelike behaviors could be exhibited by dust particles suspended in a plasma under conditions that could exist in space. So basically, when the dust became charged, they would self-organize into these like microscopic helical structures, and then they offered I'm quoting here, a rough sketch of a possible model, so lots of grains of salt, of helical grain structure reproduction. So technically, they could reproduce, which at that point, it is technically life. That's basically just dust and plasma, which is pretty awesome.
I mean, it's a lot of cool words put together.
It is.
But at the end, it's just like sand.
It is. I don't really know what the end goal here would be. I guess it's just like more dust and plasma. I guess theoretically they could develop some sort of structure that could lead to intelligence, and you get like the
more dust and plasma, more dust and plasma.
Basically, this is like on Star Trek when they were too lazy to make an alien thing, and they just had like a light that lit up behind like a sheet. Yeah, it's like that. Like it's technically feasible. Is kind of what I'm saying, which is pretty cool. So, I guess overall, my main point here is that without carbon, there's probably not life, but technically there could be. Maybe.
That's better than Marcus's outcome.
That's true. That is true.
Yeah, I said no, you can't have any life without the hydrogen. It's just not happening.
It is possible. It is technically possible. Kind of. So, Chris, what did you do?
So for my answer, you guys looked at like super really important elements. I did not. I went the opposite way. All right,
that does it for our show today.
So I looked at the 24 synthetic elements on the table, and synthetic element means that it doesn't occur naturally. So we have to synthesize it in a lab, and that's how it's created. And obviously, they're not really that essential because we didn't live with them before we created them. But I wanted to see if like they do have any sort of lasting impact. Like if we never created it, would our world be different today? So the range covers from atomic weight 95 to 118. So to start, I looked through history to see like what the first synthesized element was, and it was technetium. It was synthesized in 1937.
1937?
Yeah, 1937.
I was actually, when I was doing this, I was a little shocked at how, like, early some of the discoveries of, like, these crazy compounds were and stuff.
Yeah.
It's pretty cool. Go humans.
We're smart.
I didn't even know we could, know we made a new element in 1937, like...
Right?
Yeah. Well, the thing is, so this element is atomic weight 43, which you might notice is not in that range of 95 to 118. So there was a gap in the periodic table that we didn't have before this. And I guess this is like an element that does occur naturally, so it's not a purely synthetic element, but it occurs naturally in such small trace amounts that like we didn't realize it existed.
Mm-hmm.
Interesting.
But since it does occur naturally, this is not what I'm talking about. I don't really care about this one. So moving on.
All right, this cool fun fact, forget about it. We're not using it.
Yeah. So the first purely synthetic element was curium, which was created in 1944. And this is in that range. It's atomic weight of 96. And they created this by using a cyclotron, which is basically just a particle accelerator.
But it's also it's powered by a standing bike.
Right. And they basically just bombarded plutonium with a bunch of alpha particles, and that's how they created this curium.
How do you get a grant for that?
I don't know, especially because this is the first one.
Hi, can we have some plutonium and, like, I guess some alpha particles we can shoot at it? We gonna try something.
And then later that year, they use a similar process, pretty much the same process, to make americium. I don't know if that's how you pronounce it. I feel like it's americium or americium, but I like saying americium because it's America.
That's why it's called that.
Yeah. And creating these two elements was actually so difficult for them. Like, the process was so difficult that they originally named them pandemonium and delirium.
That's great.
I guess they just got, like, fed up with it.
Yeah, how salty do you have to be that the new element that you create in your laboratory, you, like, sarcastically name, like, delirium?
Yeah. And then the most recent element that we discovered, or that we created, was tennessine, or tennessine. It's like Tennessee, but instead of the double E at the end, it's I-N-E. So I guess tennessine. Tennessine?
Tennessine works.
Fine.
Yeah, I'll go with that.
Yeah.
This is the only 10 I've seen. I don't know.
Anyway. See, now my doo-doo joke isn't the worst joke on this episode.
Yep. This is what I'm here for.
We're here to lower the bar over and over and over again.
So, as I said in the beginning, my goal is to see if these elements were useful at all. So I looked at a few practical applications that we've come up with for some of these. And the first one I looked at was americium. So americium is used in a lot of, like, the common type of smoke detector uses americium.
Really?
And, yeah. So the way it works is that they run an electric current through the americium, and when smoke comes up and goes into the detector, the americium absorbs the smoke, and that disrupts the electric current, and that sets off the alarm. Now, there are other types of smoke detectors. There's optical smoke detectors as an alternative, but the americium smoke detectors are cheaper and they're more sensitive. So that's one use of one of these elements.
So if your smoke detector's going off all the time, even though you're just cooking, you're cooking one goddamn pan, it's not even going wrong, americium is to blame.
Or if you walk in, your smoke detector's watching The Notebook for like the 4th time that week, it's probably americium.
Oh, because it's very sensitive?
Oh, I did not get that joke right away.
I'm just really dropping that bar as low as possible, guys. I'm sorry.
You must have been thinking that joke for a while, because it was like forever ago you said it was sensitive.
I was. Freely admit it.
It's like, God, they need to shut up so I can make my bad americium sensitive joke.
He just says it in the middle of our would you rather. And then americium is also used sometimes as fuel in space because it has a really high rate of nuclear fission, which creates a lot of energy, so they can use that to propel things in space. One of the reasons why it's not really widely used is because it's very scarce. Like, there's not a lot of it.
Well, yeah, we're making it.
Yeah, we have to make it, so you can't just find it. And there are a lot of alternatives to all these applications that we use for it, so it doesn't really have a huge impact if Americium disappears, unfortunately. So I moved on to the next one, and the next one is californium. And californium is a very strong neutron emitter, so it just like shoots out a neutron, like a bunch of neutrons. That's like
It's just all the time.
known property. Yeah.
Only known property. It shoots neutrons out. We can't get close. Someone help! We're ducked behind the desk, but we can't get out.
So it shoots 1 microgram, or no, one microgram of californium produces 139 million neutrons per minute, which I don't have anything to compare that to, but it sounds like a lot.
It's a big number. I'll freely admit that.
Yeah.
Problem is all big. Once you get down to like molecular stuff, it's all big numbers.
So because of this property of it, that it has, it's very useful as like a neutron startup source for nuclear reactors. So like for a nuclear reactor to start up in a stable, safe way, you need a lot of neutrons to like hit it. I don't know the exact process, but they need neutrons to hit it.
Need more neutrons.
Yeah.
More neutrons, more plasma, more dust. I like that the safe way to start a nuclear reactor is to drop like a veritable like chemical machine gun into it.
Basically. Another use of californium is it's a process called neutron activation analysis. So it basically it's a process that you can detect concentrations of elements in a sample. So if you have a sample, you can tell how much of one element is in that sample. And then another process is neutron radiography. Radiography,
yeah.
You say the word and then you realize right after you finish saying the word that it's wrong.
Well, Ben doesn't. Ben just says it wrong and then thinks he got it, and he's like,
Nailed
yeah, first
it.
try.
Yeah, first try. And this process it uses the ability of neutrons to penetrate materials. So they use it for like aircrafts and weapon components, and it helps them detect corrosion, bad welds, cracks, trapped moisture, stuff like that.
Interesting.
Yeah, so those are like the 3 main things that californium is used for. The thing is, there are other elements that also shoot off neutrons. Californium isn't the only one. So there are alternatives. So again, californium, not a huge impact if it disappears. So moving on to the next one. Number 3 out of 24.
I really hope we don't have this long for all of them, Chris. Just gonna throw that out there for my own personal health and mental well-being.
Number 3 is curium. And curium
Cures everything. All right, number 4, hit me with it.
So curium can also be used as a fuel in space, but it's not really a practical fuel because it produces a lot of harmful radiation, and that radiation needs to be shielded, so they don't really use it that much for that. But it does provide a very good source of alpha particles. So I mentioned alpha particles before. That's how curium was created. They shot alpha particles at plutonium. So we can do that with curium now. We can shoot stuff with alpha particles.
You can make more curium and then shoot more things to make more curium.
Yeah, you could if you wanted to.
More dust, more curium, more plasma, more neutrons.
So they use this alpha particle property in a device called an alpha particle X-ray spectrometer. And what this does is it identifies elemental compositions of samples. And they use this commonly in space, like taking samples in space and planets and stuff. So I didn't quite understand exactly how it worked. I think they hit a sample with alpha particles as well as X-rays from a radioactive source. And then that scatters alpha particles from what you're hitting it with. And then they analyze those scattered alpha particles, and they're able to tell what the composition is from that.
Oh, yeah. That's like, it's like why the sky is blue, because of how the odds of different particles interacting will result in a certain pattern.
Sure, I'll go with that.
Just help it. I know all these things now from this podcast. It's great.
Yeah. We never covered why the sky was blue, did we?
I must have.
That's just something you know.
Oh, I might have learned that in college when I was doing my modern physics course.
How has that never come up?
It'll come up at some point.
Yeah.
Anyway, so this alpha particle X-ray spectrometer is on like a lot of different rovers just because of space exploration. So it's on the Spirit rover, which was on Mars, and they used it to take a bunch of samples on Mars, and we actually learned the chemical composition of some rocks on Mars because of curium.
That's both the coolest and least cool thing ever.
Yeah,
Right.
Like, all right, we found out the chemical composition of these rocks
on Mars.
on Mars. Yeah.
And the Spirit isn't operational anymore. They ended contact with that. But the successor to the Spirit, the Curiosity, also has the same device on it. And that is still operational. So they're still using curium up on Mars. And like the previous two, there are other elements that have this alpha particle source property. So not a big impact if it disappears.
All right.
So moving on to the next 21. None of them have any practical use.
The other 21 suck.
The other 21 had no practical use. I went to their Wikipedias, all their Wikipedias say, in the application section, it says the only reasonable application is in scientific research.
Which is a really like nice way of saying this thing immediately like destroys itself upon creation and only
Right.
Yeah, a lot of them have like really, really short half-lives. So they like just disappear right away or like turn into a different element. So unfortunately, or I guess not really unfortunately, if any of these disappeared, it wouldn't really affect us. I think that's sort of comforting after both of your guys' answers to know that we wouldn't all die.
I let us have a universe. That was my big. I
did
had
let
to
us have a
try to get
universe.
there. I almost gave up and just said there's no universe and just would have gone through all the things, but concluded that there was no universe anymore. But for the people, I saved the whole stinking space.
So I have a would you rather for you guys this week.
What? Flipping the script.
Yeah, I know. Stealing it from Marcus, stealing his thunder.
You can have my thunder. I think it's probably mostly made of hydrogen anyway.
Hey.
Hydrogen Thunder.
Ooh, that's a cool band
It
name.
is a cool band name.
Hydro Thunder was an arcade game back in the, I guess, 2000s. It was fun. Anyway, continue.
Bonus fact.
This fun video game fact brought to you by Benjamin Storms, resident video game expert.
Yay.
Okay, Ben.
Yes.
Would you rather grow hair 10 times as fast or be completely hairless?
So, okay. So, just to be clear,
Yes.
this hair growth is on all parts of my body, correct?
It's just all the hair that you have right now grows 10 times as fast.
Yep. It's kind of what I was afraid of. Oh, man. So, I think I got... that's tough.
So to put it into context, I guess, so I get my hair, the hair on my head cut like once a month. So
Yeah, I think that the hair on your head grows roughly an inch a month.
yeah, so I would, instead of getting it cut once a month, I would probably have to get it cut once every 3 days.
3 days.
I mean, to maintain, you could also
To
just do like a
maintain.
longer do and like go a few more days.
Yeah.
Right.
So,
But then you have to change your style, I guess. But
Well, you can just like go through. You can just go like, let it go long and then cut it short and then let it go long and then cut it short. And you could probably get like,
then like beards grow, because like some people shave every day, just like normally.
yeah, that one's gonna be trickier.
yeah.
Here's the way I'm looking at it. Like, assuming you do the amount of maintenance is normal, but you're either a very hairy boy or a very hairless boy, there's gonna be a subsection of the female population that's attracted to either one.
Hair will be, yeah.
So there's gonna be girls who really like the hairless. There's gonna be girls who really like the hairy. And the question is, which one of those do you want to be your options?
So the one problem with the hairy is that we're not just concerned about your facial hair and head hair here.
Right, there's more types of hair.
There's more types of hair that could be problematic.
Ugh, nose hair. Damn it.
Yeah, that's what we were
Yes,
thinking.
that's the one that I'm referring to.
Whatever, man. Just let it grow down there. We don't have to talk about it. That's not like gonna ruin
but
your life.
You're kind of pushing in a direction that involves talking about it. So, I mean, it's not insurmountable, but it's going to require maintenance.
It'll be a lot more work, and you'll probably spend a lot more money on haircuts.
You will.
Is it a sign of how lazy I am that I would consider going hairless over regular hair just to avoid having to do like, going to get my hair cut every once in a while?
No, that is 100% the selling point. No, I understand.
Yeah, that's a legitimate thing.
There's actually a condition where you're hairless.
Yeah.
That is a thing.
Yeah. And so I think you get like, especially the people you get used to that pretty quick. And I don't think it's that
You just have to turn it into
crazy.
your style. You just don't have as many options in terms of fashion.
The nice thing about having the fast growing hair, like there are maintenance issues and things, it lets you be much more ambitious with like costumes and stuff.
That is true.
We're coming up on Halloween. Think about like,
or if you're like a cosplayer or something.
right,
an
it'd be
actor.
cool if I could or an actor. That's actually very true. Yeah. If I could be, look like this person, well, but my hair has to be considerably longer. Well, I'll just wait like a week, and it is. Ta-da!
I think some actors actually keep their hair long until they like get a role, just in case.
Yes, they have the hair they need
Yeah.
at the time they need it.
Do any like of the hair removal options like permanently remove the hair? Like,
I feel like there's like doesn't like laser hair removal isn't that it's not permanent, but it's definitely longer than shaving and or waxing.
because if you could just like go through like one time like a big procedure that you're in there for a while and it sucks, but they like remove the problematic areas of hair and you just keep what you think you can deal with.
I don't know if that exists.
I'm Googling. Okay, so laser hair removal lasts 6 to 12 months, apparently. After 6 to 8 treatments, you can expect a marked reduction in hair, and a regrowth can be managed with touch-up treatments every 6 to 12 months. So you could do that.
So now it'll last about like half a month.
Yeah, but it'll be pricey.
Yeah, I think I'm gonna go hairless just because I'm still in my head debating between my regular life and the hairless, and it's kind of close, and the being hairy is not in that competition range. So I think it's gotta be the hairless for me.
Yeah, I think I agree. It's just gonna be a lot of work.
I agree too. Like dealing with your hair is a big life change. Like you have to change a lot of things that you do. You don't have to change anything if you're hairless. You just look different.
I'll just get wigs.
Yeah, you could just get wigs.
And you go so much faster down a slip and slide.
You
Yeah,
could be a swimmer.
Whoosh!
we are smooth boys here.
Yeah, that's what. Come back next week when our podcast is named Smooth Boys.
Yep, smooth boys. Sorry, guys. Rebranding.
It's episode 69 next time.
Episode 69, Smooth Boys.
Smooth Boys.
Oh, no.
Oh my god, that's too much. But seriously, if you don't want us to actually become the Smooth Boys podcast,
Don't worry, it will never fucking happen.
part of what keeps this show going is all our wonderful hypothetical questions that we have on our big spreadsheet. That said, it is starting to run low again, and every time that we add more questions, they sometimes are good and sometimes are terrible. So if you want to help us maintain our beautiful list of hypothetical questions and get your silly question answered on our show, send us an email. Shoot us an email at absurdhypotheticals@gmail.com, and we will be more than happy to answer your question like we did today for Luke Aschenberg.
Yeah, that's what he did. He sent us an email and we're like, oh, that's an awesome question. We're going to answer it on the show.
Mm-hmm.
And if your question is not good, we will work with you on it. Like if it's something that doesn't quite fit the show, but we like the we can work with the idea, we'll shoot you back and be like, hey, we want to do it. We want to do it this way, and we can go back and forth, and you can kind of help shape the show that way.
You can be a part of the process.
Mm-hmm.
So do that. Super cool way to get involved with the show. Helps us out. We love getting them. So it's positive, win-win all the way around. So next week is not a listener question, but is a special for our Halloween episode.
Spooky.
We'll be answering, how would you survive the zombie apocalypse on a budget?
Spooky.